So for today's lecture on introduction to CAE simulations, a free bootcamp, certified bootcamp webinar. So yeah, so as I mentioned earlier, for the people who joined just now, right? So all the queries, concerns you guys have, please do put up in the chat box. At the end of the meeting, we'll have a Q&A session where I'll answer all your questions. Okay, so talking about today's contents, right? So today we'll start basically with all the prerequisites. So what is required for you as a CA engineer? Okay, first we'll see what CA, its significance, the scope. Okay, we'll also look into all the various industrial examples which we which are used by CA, all the applications, and then we'll move on to all the various types of analysis. Okay, so we'll discuss about what is a static analysis, what is a dynamic analysis, what are linear, non-linear analysis, what is meshing, why is meshing required, all the process involved in meshing, the boundary conditions, all the loads, constraints, and everything. Then we'll discuss about we'll have a software demo where we'll work on a simple bevel gear simulation in ANSYS Workbench. Right, great. So as I mentioned earlier regarding the prerequisites, so as a CA engineer, so if you're willing to go for a job, or you want to, anyone, if you're interested in pursuing a career in CAE, so the engineering basics in the sense, all the concepts in engineering mechanics. Okay, all the applied concepts regarding all the degree of freedom, your rigid body motion, your friction, all the fundamental physics, the understanding of engineering fundamentals, followed by strength of materials, where you'll basically have to understand an overview on all the stresses, strains, all the metal properties, beams, shape force diagrams, bending moment diagrams, all the other concepts related to that. Then you'll also need a fundamental understanding on FEA. What is FEA? How things work, how solvers work, all the very fundamental things. Okay, apart from that, you'll also require plenty of tool knowledge and communication skill as well, which I hope you guys will keep developing in your career, right? Yeah, so moving on to the part, so what is FEA, right? So many people ask what is FEA. There might be people here who might know what is FEA. There might be people who might not know what is FEA. Just to give a revision, so FEA is actually a numerical technique. Just remember this key point: numerical technique, where we actually have a physical model and we try and discretize this model into finite number of nodes and elements, and we try and apply boundary conditions to get approximate results. Okay, I'm repeating, these 2 points are very, very important. FEA is a numerical technique. Okay, and then we basically get approximate results out of the simulation which you get. Okay, why approximate is because I'll tell you. Okay, so during, let's say, the physical model which I mentioned, right? For example, if you can see here, we have something with like a sphere shaped object here. Okay, where what we are doing here is we are trying to convert that model into finite number of nodes and elements. So this particular element, as we call it, if you can see, it has 4 nodes. So all these 4 nodes, if you connect together, form an element. Okay, and this element is actually called as a quad element. Okay, and if you can see, we are just approximating the particular sphere from a infinite continuous domain to a finite discrete domain. So this process is what we call as meshing, and upon meshing and converting this physical model into a numerical technique, so we basically get what we get: approximate results, right? So yes, so if you see methods of engineering analysis, right? So any engineering problem you take, it can be solved using 3 methods. So one method is actually your experimental method, your analytical method, and your numerical method, right? So talking about your experimental method, so usually anything which we do physically. For example, let's say you are having a simple cantilever beam, or let's say if I talk about things in a bigger scale, let's say you have an automobile car. Okay, where you want to try and analyze the safety of the car when in an event of crash. So what we'll do, we'll basically have a car where we'll try and crash that car to to try and experiment on the same to analyze what is happening to the passenger. Okay, so I mean, of course, we'll not have real passengers. We have something called as dummies, which are human replica of human, which is a human replica of which is going to sit inside the car. So we'll basically try and experiment to try and get out the results out of various different experiments and iterations, right? The results which you get out of that is what we call as experimental methods. And then we have analytical methods, where we try and calculate all the things, all the let's take an example. So let's say you have a cantilever beam, or let's say a simply supported beam. So if you want to try and find out the deflection, the stress produced, the strain produced in the cantilever beam corresponding to a particular loading which is there. So basically you'll have to use formulas such as, for example, in the cantilever beam, as I mentioned, so the deflection formula is going to be PLQ by 3EI. Okay, and then you similarly you're going to have you're going to use the bending equation to find out the stress. Okay, so based on all these predefined formulas and theorems, if you try and find out the results, that is what we call as analytical results. Okay, and then so you're going to have numerical methods. So where numerical method is something like we actually try and use different techniques such as functional approximate method, finite element method, the finite volume or difference method, to basically try and get results numerically. Okay, for example, if you can see here, so usually the functional approximate method and finite element method is the most commonly used method in finite element analysis, whereas finite difference method and finite volume method is used for CFD applications, computational fluid dynamics application, where we try and analyze fluids, right? So we'll discuss or we'll deep dive into what is functional approximate method and what is finite element method in detail. So in functional approximate method, we have our variational method and weighted residual method. Okay, so talking about variational weighted residual method, so let's quickly take an example of a some case. Let's say you have a let's say you have a simply supported beam. I'm sorry. Okay, which is having loads at the center. Let's say there's a load P, and this end is A, this end is B, and we have the length of your beam, which is like, let's say, L. Okay, now if you want to try and, so what is going to happen upon this application of load, this beam is actually going to have a bending, where this is going to be your measured amount of displacement. Okay, and correspondingly we'll try and find out the stress and the strain and the amount of deformation and everything. So when you want to try and find out, so using if you are using this particular functional approximate method, or let's say variational method. So in functional approximate, as you can see here, you have variational method, where we have a method called as Rayleigh-Ritz method. Okay, so in Rayleigh-Ritz method, I'm not sure if you're able to see my mouse. Yeah, so in Rayleigh-Ritz method, so what we do is basically we assume the concept of I mean, so we assume the concept of potential energy, where let's say we take the potential energy as pi. Okay, and then we assume that the potential energy is actually equal to your internal energy and the summation of work done. Okay, so where let's say, I mean, not the internal energy, sorry, your strain energy and the work done. Okay, now what is strain energy? In any case where we apply loads, right? So if you might have gone through the stress strain graph for various materials, so you might have a understanding that any component if it is under loading, and we try and remove the when we try and remove the external load before your elastic limit, your material will regain it back to its original shape. I mean, it will regain, it will have the ability to basically regain back to its original shape. So this property of the metal is what we call as elasticity. And how does this particular if you see carefully how this material comes back to its original shape, you'll understand that this is because of the strain energy which is stored in the component. Okay, now basically strain energy can be termed as the amount of energy which is stored in the component because of your external load which is being applied. Okay, so whenever there's a load which is being applied, there is going to be some resistance offered to this applied load, so that it doesn't I mean, your component always tries and sits down in equilibrium state, right? So when this happens, there will be if you see in atomic level, or if you see in microstructure level. So what happens, there'll be covalent bonds between every molecule. Okay, all these covalent bonds, when this load is being applied, so they'll actually try and deform, and due to this deformation there will be some amount of energy which is stored, which will be stored. Okay, and this energy which is stored, which is used to actually regain back your component from your deformed state to original state, is what we call as strain energy. Okay, and then similarly you have your work done. So work done is basically your force into displacement. So that's what is work done. So we assume the concept of potential energy, where we try and find out the inter energy. Now if you want to calculate inter energy as per this Rayleigh-Ritz method, okay, so as per this Rayleigh-Ritz method, so you'll basically have to use formulas. For example, you'll have your inter energy formula, which is EI by 2 into 0 to your limit, which is your length of your cantilever beam, followed by d square x by d square y by dx square whole square into dx. Okay, which will give you your inter energy, where this y is actually nothing but your trial function. Okay, which can be taken as a polynomial or as a trigonometric trial function. For example, if I take an example of a polynomial trial function, the trial function will look something like this. Okay, so the more higher number of terms you have, the higher will be your accuracy of your problem. Okay, now post we try and analyze this, what we'll do is we'll basically differentiate this twice with respect to x. So we'll find out dy by dx, and then d square y by dx square. Then basically we'll get this, and then we'll square it, we'll apply limit 0 to L, and then finally we'll come up with this inter energy formula, right? I mean, once we get the inter energy, we'll find out the work done using the force and the displacement, and then we'll try and apply in this equation to get our inter energy. And at the maximum, at the point of maximum deflection will be where your will be where your potential energy will also be highest. So you will we'll assume the concept of minimum potential energy, where and then we'll again try and integrate it to find out your displacement of this particular cantilever beam with certain formula, right? So such kind of method on using assumptions and using these kind of concepts such as potential energy and your trial functions and everything is what we fundamentally call as this variational method. And yeah, the method which I showed in variational method is what is an example of Rayleigh-Ritz method. Okay, similarly we also have weighted residual method, where we do have 4 different methods, such as point collocation, subdomain, least square, and Galerkin, where we try and have residuals, weighted residuals. We have a particular equation, we try and bring it down to a integrate and bring it down to a smaller value, and then we compare the residuals which are there. We try and look for convergence, yeah, and basically you get answers, right? So such method is what is all about dealing with weighted residual methods, right? So now yeah, so okay, so I mean, is my voice audible? Right. Okay, I was having some questions in the chat box for voice. Right. Great. Yeah. So moving on, as I mentioned, so any problem which you take in FEA, so they have to be considered as this, right? So for example, any step which you have in FEA, which is FEA is nothing but your as I was mentioning here, if you see your finite element method. Finite element method is what is I mean, what I'm going to talk about now, right? So as you can see here, the steps involved in your finite element analysis, basically the first step is your physics, the second step is your pre-processing, the third step is your solution, and the fourth step is your post-processing. Okay, so talking about the physics of the problem. Okay, so earlier we saw about the case of a cantilever or a simply supported beam. Now if we scale up the examples, okay, a very good example of a cantilever beam would be a crane. Okay, now if you see the crane, basically you'll have loads or on one end, you'll have supports on the other end, where we'll try and lift the component and basically move that weight to a particular location, right? So if you try and understand, so where my I'm going to load the component. Okay, how much how much force will I how much counterweight should I have to lift that particular load. Okay, so what is the direction at which my crane is going to move. Okay, where are my fixed supports going to be. So understanding all these things is all about physics. So if you see here in the crane example, so here you'll have a tensioner. So here basically you'll have a big rope, where you'll have your loads here. Okay, and then basically you'll have counterweights on the back of your crane. Okay, so to try and support this particular applied load. At the same time, here in the bottom, so you'll have a this particular column. So we call this as column, we call this as boom, right? And you'll basically have a concreted base where fixed supports will be provided. And this particular boom, if you see, or the cantilever beam in case, so it will be able to basically your degree of freedoms will be your component will be able to move in this direction. Similarly, there will be a boom which will allow your motion to be happening in this direction. At the same time, you'll have a motor set where you'll be able to have the arm rotated about this particular axis, right? So understanding all these kind of things on how it is going to work, what is the nature of the problem, is what I mean by physics. Okay, another example, if you see, let's say I'm taking a particular let's say I'm taking a particular block or a car, and I'm actually trying to crash this car into this particular wall. So what is going to happen now? This particular wall is going to be fixed. Okay, this particular you know if you the car or the box which I see here, I'm going to have to apply a velocity in a direction. Let's say this is x, y. So I'll have to basically apply a displacement or a velocity at certain value on this particular direction. And then I'll have to also understand that, okay, upon crash, my crash box will actually basically it will try and crumble. The there'll be intrusion in the sense there'll be reduction in my length of my compartment. Okay, all these things I'll have to understand and figure it out, right? So these are all what I mean by physics, right? So then you have your pre-processing of a model. Okay, so pre-processing. Okay, so pre-processing, as you can see, we discussed about something which is called as meshing, right? Where basically we had a surface where we tried and we converted that as a small number of finite number of nodes and elements, which is what is all about pre-processing, right? So talking more in detail about pre-processing, any component which comes from a design engineer to a CA engineer, the first thing we'll do is we'll try and import that component into software such as pre-processing software such as hypermesh or answer, or answers, and then we'll try and pre-process the component. The first thing in pre-processing is basically something called as inspection, where we'll try and inspect the whole component for errors, for missing surfaces, damaged surfaces, deformed surfaces, all the unnecessary surfaces, all the errors in the geometry. And then the next part in the pre-processing will be your it'll be your geometry cleanup, where we'll try and clean up all the issues which you found in the geometry, I mean in your inspection. Okay, now post this geometric enough, we'll do something which is called as mid surfacing. Now mid surfacing is a concept which we usually use to try and reduce your simulation time, try and reduce the cost of the simulation. Also there are other advantages uh, you know because of mid surfacing. Okay, so mid surfacing is a concept where you have a 3D geometry which is having a thickness of either less than 6 mm, or let's say the thickness to area ratio is less than 1/20. Basically we'll go for this problem which is called as mid surfacing, where you will have a surface, thick surface. We'll try and take the mid, we'll convert this 3D problem to a 2D problem, and then we'll try and proceed with the problem. Okay, now mid surfacing is also a part of this pre-processing. Then we'll basically go for something which is called as meshing, as I mentioned earlier. And post meshing we'll do a lot of checks, connections. Connection is like so let's say your laptops, your phones, your tables, anything you have. Okay, all these must have various different parts. Now how are all these parts connected? They are all connected either by using fasteners, or using glues. Okay, or using any other type of connection material, right? So such as wires and etc. So when you try and import this particular design into your software, you'll also have to make sure that all these connections are provided, such as your bolted connections, such as your fasteners or rivets, springs, all these things you'll have to basically give. So that is what is connections, right? Now post connections, you will basically have this boundary condition application. Okay, your your case setup, which we call as case setup, the boundary conditions, the control cards. Okay, how much time my simulation is going to take. Okay, what is the duration at which my component is going to take to lift this component. Okay, so what type of analysis I'm going to do. So all these decision and everything is all covered under pre-processing. Okay, now in the next part, which is solution. Okay, so basically any solution, as I mentioned, all these earlier, if you see, all these things are converted. The physical model is actually converted as numerical technique, right? So which is all using a numerical technique. Now numerical technique involves conversion of your component or your nodes and elements into partial and differential equations, right? So after converting this, what you'll do, so you'll have to basically solve all these equations which you'll have. Okay, so to solve this particular equation, there is something which is called as a governing equation, which is actually used to solve this problem. uh, for instance, the general governing equation which is used for most analysis is this: mx double dot plus cx dot plus kx equal to f of x. Okay, where m is actually your mass, this is your acceleration, this is your damping, this is your velocity, this is your stiffness, this is your displacement, and this is your external forces which are being applied. Okay, so now if you see acceleration, which is x double dot. X double dot is what? Acceleration, as you can see, it is a rate of change of velocity with respect to time. Okay, what is velocity? Velocity is rate of change of displacement with respect to time. If I say take displacement as dx, dx by dt will give me my velocity, or for instance d by dt of my x will give you my uh, x dot, which is my velocity. And d by dt of dx by dt, rate of change of velocity with respect to time, will give me my acceleration, or d square x by dt square can also be taken as here in this issue system, right? So and then similarly, mass is your mass of the component. Damping is where we basically use dampers, or in case of you having forced vibration problems, we'll basically consider this damping. Sorry, free vibration problems, we'll basically take this damping. Okay, and then and then you have your stiffness of your component, the displacement, followed by your external force. So this, based on this particular problem and based on the type of analysis, we try and solve your problems corresponding to corresponding to your physics, and physics of the problem, and the solution which you need, right? Now post solving for all the results. Now solving means basically using these equations, you will try and compute all the results. For example, here first you have acceleration. From acceleration you can compute velocity. From velocity you can compute displacement. From displacement you can compute strain. From strain you can compute stress. How? Acceleration, if I differentiate, I mean if I integrate, I'll basically get acceleration, velocity from acceleration. From velocity, if I integrate, I'll get displacement. From displacement, if I integrate, I mean not integrate, so if I have my displacement and I compare it with original length, I'll basically get my strain. Okay, and then correspondingly, if I use the Hooke's law, which states that stress is directly proportional to strain, where if I remove the proportionality constant and put a constant, which is Young's modulus, corresponding to Young's modulus, I can easily get my uh, stress, right? Yeah, so this is how I'll basically try and compute all the solutions. And then basically I'll have my post processing, where all the obtained results are actually post processed, meaning I'll analyze whether this just value which I've got is good or bad. Okay, I'll analyze whether my strain value I've got is real or unreal. Okay, I'll plot graphs. Okay, I'll plot contours. I'll see animations on how my component is behaving. Okay, and then I'll basically validate my results and document. So all these are what are into pre-processing, sorry, post-processing, right? uh, Great. So then comes your fundamental steps in pre-processing, as you can see here. So I mentioned, right, so basically we'll discretize the structure. Now talking about discretization, right, so you might always have a question on why we need discretization, right? So think about it. Okay, when we move on to this meshing part, I'll explain in detail on why we actually need meshing in real case, right? Yeah, so as I was mentioning, discretization is nothing but meshing. then you'll basically select an interpolation function, and then you'll form your element stiffness matrix corresponding to your load vectors, and all your will correspondingly form a global stiffness matrix. You'll apply a boundary conditions. After you apply a boundary conditions, your stiffness matrices will reduce to a set of simultaneous equations, which with which you can easily try and compute all your strain stresses, and correspondingly interpret your results of it. Right. Now if you see the significance of CAE in general, okay, uh, as we saw the case for a cantilever a simply supported beam. Now if you want to try and compute your displacement, right, or let's say the maximum deflection, the deflection can only be computed at the area where it is maximum, or in case of a cantilever beam, the reflection can only be computed at the free end. It cannot be computed at every point in your system, right? So in order, if you want to compute stress, strains and deformation at every point in your system, it is going to be really really hard, and that's one of the reason why we use softwares, where we can easily generate the physical response of the system at any location which we want. Okay. And then when you're talking about computing things manually, or let's say analytically, okay, so it is really really difficult to try and predict the destructive nature of your component. Okay. Destructive nature in the sense, for example, we can never know upon the loading condition when your material will fail, okay, or how your material is failing. Okay, if you want to try and find out the stress, we'll only know what is the maximum stress we are getting. Okay, and if you compare that amount of stress with your material's ultimate strength, you can only assume whether the material is failing or not. But how it is really failing, is it failing because of stress, is it failing because of strain? Okay, so you have 5 different theories of failure, right? So all these theories of failure define how your material fails correspondingly, right? So you really cannot predict that using analytical results, whereas when it comes to simulations, you can easily do that in just few minutes. Okay, so then impractical loading conditions and failure modes cannot be computed in analytical problems. Okay, for example, let's say you are designing a flight. Okay, now if you really want to do a crash test on a flight to understand whether the crash test, or let's say crash landing on a flight, to really try and understand whether your passengers inside are going to survive or not, it is really not possible in case of doing that in case of a experimental result, or in case of a analytical result where you mathematically sit down and calculate life, right? So if we could have come up with analytical problems to try and calculate life, then for sure we humans could have evolved to such a manner that we will eventually predict the exact number of days we'll live on earth. Okay, exact time and date when we'll we'll pass on, and etc. Right, so it is really really not possible, right? So for that particular case is why we have software where we try and simulate all those things with the help of tools, right? So again, so this all comes under impractical loading conditions, because if you want to do a crash landing on a flight, right? So the flight itself is going to the just one particular iteration of a crash landing itself is going to cost you millions and millions of dollars, which is very very highly, it's very highly costly, and it is time consuming as well. So you make one small mistake in this in the crash, and you will not get the exact results on what you want. You cannot repeat the same, right? So that's where you can use softwares where you can run any number of iterations you want, and not even a fraction of what is going to cost in real life is going to actually cost you in this simulation environment. Okay, and then similarly in analytical results, it is not possible to actually you know uh, visually see, or do simultaneous calculations of various physical parameters such as stress, temperature, etc. So in analytical result, you will only be able to see how much amount of stress you've got or deformation you've got, but you really cannot see visually see how much stress it is there, and all these things, right? So that's really a a good significance of CAE. And then you have your investment. So again, so calculation time and your amount of cost involved is going to be very very less. I was explaining the case of a flight crash, right, where the simple one iteration is going to cost you around millions and millions of dollars, where a simple simulation in your system is not even going to cost you a fraction of what is going to really be there, right? So those are all the significance of CAE. Now if you see your applications of CAE, right, so there are plenty of applications of CAE. One such application is your manufacturing, I mean, which is in your manufacturing industry, where you can use CAE for various forming simulations. So in the right side, if you can see, you have an example of a forming simulation where there is a punch, there is a die, and in between, if you see, this is your workpiece. Okay, now this workpiece is actually formed corresponding to how my die is. And basically, if I want to try and compute all these stresses, the amount of deformation, all the residual values of all the things which I want to compute, I can easily compute using this answers. Similarly, on the left side is a very good example of a mold flow simulation using the mold flow software, right? So that most of plastic components, most of what you see in and around you are made of plastics, right? Even inside an automobile component, most of what you see touch are all made of plastics. Your instrument panel, or your dashboard, your side trim panel, this is an example of a side trim panel, where you have your place where you have your woofer, okay, where you have that door latch to open your door. Okay, so all those things. Okay, so similarly your handrest, okay, your switch panels, your P-pillar covers, most of all these things are made of what? They're all made of plastics. Now how are plastics manufactured? They're manufactured using injection molding, right? Now this is an example of a injection molding tool, which is used to manufacture this particular side trim panel, right? So again, this is a very good example of, or this is a very good application of how CA can be used in real life, right? So because of this, you can easily simulate and understand where my defects are, how can I improve those defects and try and change. Okay, because let's say once the die is manufactured and once it is out for mass production, and during production, if you see that there are defects while producing, it is really going to be costly, where you'll have to again change your dies for whatever number of injection molding units you have. Okay, at the same time, you'll also have to redesign your components such that this defect doesn't come back. So where you can save a lot of time and money, right? So this is a very good example of a application here. And then you have various automobile applications which are used in CAE. Okay, if you can see in the left, as I was mentioning, this is what is an example of a dummy model, right? So here as you can see, in an event of a crash, this is actually a female dummy with a body mass index of 22, whereas this is a female dummy with a higher body mass index of 35, right? So as you can see here, this is your airbag, where in an event of crash, you can try and analyze what is the effect of this crash, how I'm going to have all the forces acting on my particular human body. How am I going to survive? All these things are typical examples of applications in industry, CA industry. Similarly, if you can see here you have your automobile chassis, where you're trying to do a frequency response analysis on the chassis, and yeah. And then a frequency response analysis, like let's say for various different analysis, various different frequencies, you're trying to understand how your chassis is behaving. Okay, because every component in life is going to have in real life is going to have its own natural frequency, right? So when the external frequency which is given is equal to your natural frequency, basically your component will resonate, right? So to try and understand that corresponding to various different frequencies, we do this frequency response analysis, which is very, very useful, right? And then similarly, I was taking the case of a aircraft simulation, right? So as you can see here, you can easily do a structure analysis on a aircraft primary structures and secondary structures to easily find out your factor of safety, the margin of safety, for various different corresponding objects. That is also a very good example of CA. Right. So now moving on to the next part of the lecture. So your type of analysis. Okay. So as you can see here, there are fundamentally two different types of analysis which are used in CAE, which we call as static and dynamic. There is also one more which is called as a quasi-static simulation, which is a combination of which comes in between your static and dynamic analysis. Right. So talking about static analysis, you have linear static and you have non-linear static analysis. And in dynamic, you also have linear static and dynamic analysis. Now if you want to try and understand the what is static and dynamic, okay, I can explain that quickly with this particular equation as example, right? We saw this equation earlier, the governing equation, right? Now if you carefully note this point, okay, you might try and understand that okay, So my based on this equation is what I try and deduce what type of simulation I'm going to do. Okay, so usually the difference between static and dynamic is simple. Okay, if your component is in equilibrium state, or let's say it is in static state, and you want to try and apply loads to understand how the structure behaves, basically that's static. Okay, in case the body is in motion, or let's say you want to try and understand all the effects of motion on your particular body, then it is simply dynamic. Okay, the other difference is that the static analysis are usually independent of time, meaning whatever loads or conditions you apply, they are independent of time. For example, the case of a cantilever beam. Okay, if I apply a force on the cantilever beam or a simply supported beam here, I only said that I'm going to apply a load. Okay, I don't have, I'm not telling you that, okay, I have a load where I'm trying to apply, 30, 30 kg of load, or let's say, 300 newtons or 500 newtons of load with respect to time. I'm not doing that. I'm only applying a standard load, static load, and I'm trying to analyze. That's a very good example of, static analysis, which is independent of time. Similarly, I have my, dynamic analysis, which are all, uh, products of time, or let's say they are all dependent on time. For instance, in an event of car crash, right? So I'll basically give my, boundary condition as velocity, right? So what is velocity? Velocity is, displacement over time, where I have a fundamental parameter, which is dependent on time, right? So all these conditions and boundary conditions which are dependent on time are usually considered as dynamic analysis. If I talk about the equation here, okay, so as you can see, acceleration, velocity, both are all fundamental properties, which has which are dependent on time, whereas my displacement which I have is not a function of time, right? So in case of a static analysis, these two terms will be ruled out, where I'll only be I'll only be having this kx equal to f of x as my equation, because acceleration, velocity, both are functions of time. So in static, I don't have my loading with respect to I mean, I don't have time dependent factors. I cannot have time independent factors. So my governing equation will change. Similarly, in case of a different based on each type of analysis, my equation is going to be recomputed and changed, which we'll see, right? Yeah, so that is what is I talk about static and dynamic. And in static and dynamic, you fundamentally have two different things. One is what we call as linear analysis, and then the other is what we call as non-linear analysis, right? So talking about what is linear analysis, right? So linear analysis, if you take the example of a strain curve, so the graph under your curve, if you can, as you can see, can be split into two parts. One is your static, and then the other is your, sorry, one is your linear part of the curve, where the relationship between stress and strain is linear. Okay, whereas in the other part of your curve, you can see, okay, I mean, sorry, whereas in the other part of your curve, if you can see here, okay, so your curve is actually kind of non-linear, right? So if your analysis is done within this elastic range, so of your, or let's say within this linear portion of your curve, the whatever results of stress strain you get is within this limit of your stress strain curve, where your material is linear, then the type of analysis can be termed as linear. Meaning most components which have elastic behavior, where upon removal of load, if your component comes back to its original shape, my type of analysis can be termed as linear. Okay, and then again, so where I have if I plot a force versus displacement graph, and the displacement graph, it is, if it is within, I mean, if it is linear, I can also say that it's linear. Okay, and also when I don't have any contact between bodies, I can also take that as linear analysis. And the left bottom corner, as you can see, is an example of a linear static analysis done on a cantilever beam, where there is a point load applied on the free end, and with on the I section of the cantilever beam, and you can see the amount of displacement which is there on your beam, right? Then you have your nonlinear analysis, so where nonlinear analysis is actually categorized in terms of three different, based on three different structures. One is your geometric nonlinearity, the material nonlinearity, and the contact nonlinearity. Talking about geometric nonlinearity, if you can see, so any component which is going to undergo a large deformation, so your component will be geometrically non will be termed as geometrically nonlinear. Okay, and then any situation, any case where your stress strain graph or the force displacement graph is nonlinear. Okay, I'll say that my material is non-linear, or let's say I'll tell the analysis type as non-linear analysis. Similarly, in terms of me having contact between bodies, okay, I'll say that my component is actually, or my type of analysis is actually non-linear in case. Okay, as you can see here in this case, okay, so the nonlinear analysis, so in the bottom, if you see here, you have a car crash simulation, a frontal car crash simulation. This component is actually a BIW component of a car called Dodge Neon, where where a typical example of a nonlinear analysis are what is shown here, right? So as you can see, I'm having contact between the bodies, internally, and I have contact between the car and the car here, which is a very good example of a nonlinear analysis. Okay, yeah, just a second. Right, yeah, so this is a very good example of what I have as a nonlinear analysis, right? So similarly, I have my yeah, similarly, I can also take examples of linear analysis where I don't see any kind of contact here, right? So contact in the sense, there is no contact between two different bodies or something, so I'm only having a static load which is not dependent on time, and I'm actually trying to get the results out of that. Okay, whereas here, if you see, uh, this particular component is actually called as a rail, and the front, which you see, you will have a bumper. Now my bumper is actually coming in contact with my own dash, place where my floor panel is. Okay, at the same time, if you can see, there are components such as this shotgun, okay, and this this A pillar, your B pillars, which are all will have internal contacts, which are very good examples of what is non-linear. Okay, and another very good example of a difference between linear and non-linear is that linear simulations will usually be of very short duration, sorry, very long duration. Okay, long duration, I mean, of course, when I say it is not dependent on time, the boundary conditions and everything is not dependent on time, but usually in real life, if you see, no such, there is no such thing as I don't have time as a factor. Okay, be it a static analysis, or be it a dynamic analysis, for sure in real life it is going to be a it is going, time is always going to be involved, because time is not going to stop, it is always going to be ticking, right? So in case of that, if you see, if I compare that, my non-linear analysis are all going to be very short duration events, where my crash, or my car crash, or any such kind of non-linearity will happen in an instant. If you see the event of crash analysis, as you can see here, right? So if you can see the time here, it's in milliseconds, right? So I mean, milliseconds in the sense, so the car crash is going to happen somewhere between 80 to 200 milliseconds in real life. Okay, which is not even a second. Okay, so as you can imagine, so all your materials and everything will fail in the fraction of milliseconds, right? And yeah, as you can see here, so yeah, so based on your standards, so you have standards such as your FMVS standards, your Euro NCAP standards, your Bharat NCAP standards, corresponding to which all these crash simulations are done. Okay, so then moving on to the next part is your meshing. Okay, now as I was mentioning, okay, so okay, so let me share my whiteboard. Okay, so talking in detail about meshing, so we were discussing about what is meshing, right? But we actually did not discuss why actually we need to do meshing for a component. Why can't there is always a question on why we can't actually do a simulation without meshing, right? So the answer is very simple. Okay, so let's say, for example, there is a surface. I'm just taking an example of a rectangular surface, right? Now if I take this rectangular surface of, let's say, x and y dimensions, and if I try and plot points, okay, now why do I have to plot points? Is because I already mentioned that in FEA we basically have a domain where we try and convert this domain into a into a discretized domain, uh, where based on the this, we try and compute, I mean, we try and change that as equations, and we compute all these things using a numerical method, numerical technique, right? So if I want to try and compute, so basically I'll have a set of number of equations which I'll have to come up with for this particular problem. Okay, so now number of equations which is going to be there for this problem is going to be the number of nodes or points which I have in the problem. Basically we call it as nodes in FEA, so that's why I mentioned nodes or points. Okay, followed by that, I'm multiplying that with the degree of freedom for every node. I'll basically have my number of equations, right? If you see the degree of freedom for every node, okay, so basically, you have 6 degrees of freedom. You have 3 in translation, ux, uy, and using, and then you have 3 in rotation, which is rx, ry, and rz, right? So in case of me having infinite number of points here, the number of nodes or points will become infinite, and correspondingly, if I have 6 degree of freedom per node, the number of equations which will be generated will also be infinite, where I will not be able to solve my problem. Okay, and then in case of me discretizing it manually and coming up with finite number of nodes and elements, okay, so I can easily bring this number down to a finite number where 1 2 3 4 5 1 2 3 4 5. I only have 25 nodes. If I multiply 25 with 6, I'm definitely going to get a finite number, right? So you're getting my point, right? So now if I have 150 equations, the solver can easily compute 150 equations in no time. It's hardly going to take a sec, somewhere between 1 to 5 sec or 10 seconds to compute this 150 equations, right? So this is why we basically do meshing, right? So similarly, talking about the factors which decide the mesh, because every type of simulation which you do is going to have different types of meshes. For instance, your mesh this type is going to be decided on 3 factors primarily, as you can see here. One is your size and shape of the model, your analysis type, and the time required to complete your task. For simple geometries, as per this size and shape of the model, we basically use quad elements. For complex geometry, you can use tri elements as examples. Similarly, based on analysis type, for structural and fatigue analysis, we use something called as quad elements. And then for casting, we use casting in the sense, yeah, we use tri elements. So where I showed an example of a mole flow, right? So here, so if you see here the case of a mole flow application, so you have your mesh which will be in terms of a tri element. Okay, then you have your crash and nonlinear analysis, where we try and use mixed elements. At the same time, based on the time, if you have sufficient time, you go with manual meshing with hexa elements, whereas if you have insufficient time, we go with automatic meshing, where we have tetra elements, right? Yeah, and then again, the significance of meshing. So your meshing actually influences your uh, speed and the speed of your simulation, and your convergence. It also has a great effect on your accuracy. Okay, um, yeah, so it also has a great effect on your accuracy. And then in this process, your component is actually continuous. If it is continuous, where we try and discretize that into a small number of nodes and elements, and which is used to actually define your shape. Okay, and also a good mesh will result in good results, and a poor mesh will result in poor mesh, where you can have convergence difficulties, which might have incorrect results and false conclusions, right? So then moving on to boundary conditions. Okay, so boundary conditions are like there are 2 different types of boundary conditions in general. Okay, now when I talk about what is a boundary condition, boundary condition is actually the information on how I'm going to load my component. Okay, where is the location of my loading? Okay, so all these corresponding to all the field variables such as my forces, temperatures, etc., are what are considered as my boundary conditions. Okay, fundamentally there are 2 different types of boundary conditions. One is my geometric or essential boundary condition, and then the other is my natural or non-essential boundary conditions. Okay, in case of a cantilever beam, which we saw earlier, so we did apply various boundary conditions, right? For instance, what is a cantilever beam? Cantilever beam is a beam which is fixed on one end and it is loaded on the other end, right? So this itself depicts the nature of your boundary conditions, the location of your boundary condition, etc. For example, on one side it has to be fixed. Now this is a boundary condition. At the same time, you have your load which is being applied on the other end. Okay, which is again a boundary condition, right? You're getting my point. These are all examples of essential boundary conditions, because without this cannot be a cantilever beam. In case I don't fix one end of the cantilever beam, then it cannot be a cantilever beam, because by nature the cantilever beam is actually a beam which is fixed on one end and there's load on the other end, right? So similarly, if you see okay, so if you see the example of a non-essential boundary condition, if I take the room temperature, okay, or the effect of heat into consideration, it is going to be non-essential, because I am only calculating the deflection or the stress produced on this cantilever beam because of this load. Okay. Also the vice versa can happen, where in case I want to find out thermal stresses, then the temperature of my surrounding will be my natural boundary condition, and the loads and everything else will be my essential bound. It will be my essential boundary conditions, the other all will be my natural boundary conditions, right? So that is what is this. So if you can see here, the very good another example is here you can see here a bar which is hanging down. So at this point, this point one is a point where it is fixed, which becomes an essential boundary condition, because for your component to be in an equilibrium or a stable state, this point has to be fixed, right? Otherwise, because of gravity, it is going to fall, right? At the same time, at point two, if you can see, there is a force in the sense, a gravity load, I mean loading because of its own weight of the component is actually in effect, which is a very good example of a non-essential boundary condition, right? So yeah, so that is what are examples of boundary conditions. Okay, now quickly moving on to the software demo. So for today's lecture, I'm going to use ANSYS workbench for the software demo on what all things we learned. Okay, so we will try and simulate a case of a uh, we'll try and simulate the case of a bevel gear simulation, and basically we'll apply various different loads, the boundary condition as one moment, the rotation, all the supports, and then correspondingly we'll try and analyze the results, right? So just give me a minute, let me quickly share my other screen. Right, so let me know when you can see my screen. All right, so this is how your ANSYS workbench interface is like. So here I'm going to do a static analysis on a bevel gear simulation. So where so since it's a static simulation, I'm actually using this static structural. All I have to do is just drag and drop this, and I'll actually get my static structural page. Now as you can see here, you have engineering data, geometry, model, setup, solution, and everything. So for the geometry, I'll have to import my my bevel gear setup. Okay, so just give me a second. I'm not sure where my component is. Okay, I have it here. So in that case, I'll actually have to open this geometry file. So if I open this geometry, I'll have something which is called as a space claim, which will be there for importing and working with geometries. Let's just give it a minute. So it's kind of loading. As you can see here in the bottom, it is showing as starting space claim, right? So we'll just wait for a minute for it to open. Now once it opens, we'll try and import our space claim file, and then we'll try and move on to the mechanical model to do the case setup of this bevel gear simulation. Yeah, so I think it's open. This is how space claim looks like. So basically I'll open my bevel gear set here. Yes, now this is how my bevel gear should look like. If you can see, you have a big gear and a small gear, which is your driven gear and your pinion, right? So I've already edited some of this bevel gear, so it will actually be a very, very big thick model. Just for reducing the number of nodes, I've actually cut it as hollow beforehand, right? So once this is done, so all I have to do is just check if I have a tick mark. If I have a tick mark, it means that the geometry is uploaded successfully. And I'll just open my mechanical model. A mechanical model is where you where you do all the setup. For example, you apply your, okay, just give me a second. Let me close this. If I close this, I'll be able to open this mechanical model. Yeah, I'm really sorry for that. Just give me a second. I'm just trying to open it again. Yes, now I think it's open. Right. So as you can see here, so it's actually kind of loading. So my bevel gear is actually, I mean, my component is actually getting transferred. So once it is transferred, I'll be able to see the setup. So I'll basically, apply, contacts, settings and everything else. And then we'll try and do a, static structure analysis, non-linear, static structure analysis here. Okay. So for the material, I'm going to use structural steel. Okay. So if you can see here, I'm already going, I already have structural steel assigned here. We want to see the properties of the material. So yes, so the Young's modulus of the material, the Poisson's ratio, the bulk modulus. Static structural material is a default material which is available in ANSYS Workbench. So all you have to do is just go out to your mechanical model. I mean your project schematic page, go into engineering data, and then just import the static structural from the set of library available. Right. So then I whatever contacts and everything else I have, I'll basically delete it. So when this component is going to rotate, right, so there is going to be physical contact between this faces of the gear and this faces of the bevel gear, right? So for that, I'll actually have to define a physical type of contact. So the type of contact is usually going to be frictional, because you are going to have friction, right? So what I'll do is I'll actually insert a manual contact region, where for the target, okay, for before creating targets and components, what I'll do is, so I'll actually select all these faces one by one, and I'll create something which is called as a name selection, so that it becomes easy for me to select. Okay, so talking about selections, okay, so for rotation I can use my middle mouse. Okay, for panning I can use my control and middle mouse, and I can scroll it. For zoom in zoom out, I can use my scroll bar to zoom in zoom out, control and zoom in zoom out. Where I'm just trying to select all the faces. Okay, and then I'll press N, and then I'm just typing this as big here. And then similarly I'll actually isolate this body, and I'll try and select all the faces of this gear and create a name selection as small gear. Great. So now I have two name selections, so big gear and small gear. So for the contacts, so the type of contact is bonded, so I want to change it to frictional contact. Okay, I'll show all bodies. Okay, and then for my contact, I'll basically use my okay, so instead of geometry selection, I'll use name selections, where for contact I'll use my this, and for my target I'll use my small gears. Okay, so frictional, I'll give a friction coefficient of 0.2 here. Okay, and then everything else I'll just keep it in program control. Let's not disturb anything. Okay, let's just change only this to add offset ramped effects, and then basically give your formulation as augmented Lagrange, and then rest all we'll keep it in program control. Okay, if there is large reflection, I think, yeah, so this is my contacts. Okay, now I'll have to provide joints. So joints are usually basically used to determine how my component is going to behave. Okay, for example, let's say this component is going to rotate. right? For rotation, I'm going to say that my component is actually going to rotate about Z axis. So I'm providing a joint, not a fixed joint, a revolute joint, which is going to have only, rotational degree of freedom among Z. Okay. And at the same time, I'll also create one face. Okay. So it's not going to be a body to body joint. It's going to be a body to ground joint, right? At the same time, you'll create another, joint to define this part of my component. Okay. I mean, sorry, this is also going to be a, body to body joint, a revolute joint, where it's also going to have rotation. Right now, once this is defined, I can easily, go on to the mesh. For the mesh, I'm going to use a standard mesh sizing of 6 mm here. And for the sizing, I'll basically select my name selection as big gear, and I'll provide a sizing of 0.75, sorry, 1.75, and another face sizing to my small gear. This was big gear, right? Yeah, this is small gear, where I'll also give a face sizing of 1.75. Right. Now I'll actually generate my mesh. Now post generation will also check for quality. Okay, if you see the in quality of this details, where we'll try and first check for aspect ratio, where my aspect ratio is pretty, big. I mean, it's almost like 34 units. So I mean, it should not be 34, right? So aspect ratio is the ratio of, your largest element length to smallest element length for the particular material, right? So yeah, so in this case, I really cannot have this. So what I'll have to do is I'll have to increase my smoothing, to just check whether my aspect ratio is actually, coming down. Yeah, so now if you can see from 34, it came down to 12, which is actually a, decent number. Okay, it's not very good, but still, the recommended aspect ratio is actually somewhere between, less than 5. But still, for this simple simulation, 12 compared to 34, 12 is actually a, decent number, right? So now post checking this, so I can quickly move on to the analysis settings, where I'll try and give 6 steps. Okay, so I'll change this to on, where I'll define this by time, and basically I'll give my, time. So my initial step as this, maximum step as, let's say, 1, and then minimum as 0.05. It's actually, I'm just using it based on previous experience. Okay, but usually, you'll have to actually experiment this to, sorry, I gave things in wrong positions, right? Yeah, so then I can also switch on my last deformation, and output request are is where, you will basically define whether you want to calculate all these things or not. So I'm going to usually keep all these output requests as yes. So I'm going to keep all these output requests as yes as of now. And then what we are going to do is, we'll basically, uh, apply the boundary conditions. Okay, so you're going to have a joint load for this rotation. Let's say the rotation is actually, we'll define it in a tabular column, where I'll provide, uh, let's say I'll provide 120 degrees of rotation in general, from, let's say, 15 or let's say 20. Yeah, yeah, 20, 40. Yeah, this is fine. All right, I'll also have to, provide a, joint load for the other gear, where this is going to be a moment corresponding to the question. As you can see, 1 e power 5. Right, so basically, I'll give this in a tabular column. The unit system is proper mm, so I'll just give it as 1 e power 5. Okay, why minus is because you have to make sure that both rotate in different direction. If this rotates in this direction, for sure this has to rotate in the other direction, such that it is proper. Now once this is done, I'll actually compute I'll basically have this whole thing compute for all my stress, my strain, my deformation, and my and all my life and but as of now I'll just compute this. Okay, so you all you have to do is just solve it, and your solver will solve. Okay, so this is how the case setup for this has to be done. Okay, I have already solved this problem earlier, so I'm just going to show the solved problem finally. So I've done a grid dependence test where I've used 6 mm mesh, 5 mm mesh, 4 mm mesh for the same bevel gear, and I've computed it. I'll show you this for one case. Okay, maybe once the recording is down to you, you guys can try and you know try and simulate the same if you want an answers purpose. Right, as you can see here, so I have my bevel gear where if you see the stress value which I've got is like 430 megapascals. The material's maximum strength, if you see, is actually I mean the uh, sorry, the ultimate strength of your material is 460 megapascals, whereas the stress value which I've got is little less than 430. So basically the deformation which I'm getting here, I can conclude that the material is going to be uh, go into a permanent deformation state where I'll not be able to regain back to the it will not be elastic basically. Right, similarly the deformation, if you can see, 47 mm of deformation, and this is my strain amount. If you see the simulation, you'll be able to see that my component is actually rotating properly as per my boundary condition. Right, yeah, so hope yeah, this is what we'll do now. Post this, we'll also try and understand and validate all these information corresponding to various different iterations and results. Right, so which we basically call as post processing, where we try and plot graphs, where we try and validate results to check whether this result is good or bad. Right, yeah, so that concludes the lecture.